All right. So we were in the thick of solving logarithmic equations. That's where we were. So all the fun of all of that. We're about to get to word problems, but I thought maybe doing one from yesterday might not be a bad idea, because this will demonstrate something that we're supposed to know. Okay. Actually, not happy with this problem either, but for different reasons. Uh-oh. I know I had that today. Shoot, where is, oh, there it is. Okay, we're good. Okay, so here we go. We have the equation. We have a 4 natural log 4ln 6 minus 7. Let's go ahead and do that. Now change that to a 6 minus 7w. Okay, so we have 4 natural log 6 minus 7w plus 2 is equal to 30. Okay, so just to kind of remind us, right, this guy, PEMDAS, remember logs count as exponents. Okay, so we're dealing with exponents, we're dealing with logs. Excuse me. It just doesn't make as nice of an acronym, so that's why we just don't worry about it. Okay, so when we evaluate, when we calculate things, we generally go, right, we go in this direction, we do it in this order. But when we're solving, we're trying to undo stuff, we do it in the opposite order. So the first thing we have to do is we have to get rid of that arithmetic. Okay, so we have 4 log 6 minus 7w is equal to 28. Then as we move up our piece here, we move up our process. We're now in the multiplication division set. So we're going to go ahead and divide both sides by 4 to get rid of this 4 out front. So we're going to have natural log of 6 minus 7w is equal to 28 over 4. That should be 7. Okay, we took care of this part. Now we get to deal with the exponent. Okay, so we need to get the variable out of the logarithm. And to do that, we're going to make the base of both sides something that's going to clear the logarithm. Okay, so whatever base the logarithm is, we're now going to make that the base of both sides. Okay, so there's a formula. I used different letters before, but a to the log base a of b is equal to b. That's the process that we're dealing with here. Okay, so in order to move the variable out of the logarithm, e, natural log is base e raised to this thing, that's just going to go back to being 6 minus 7w is equal to e to the 7th. And there's really not a whole lot you can do about that. Okay. I mean, we could type it in the calculator and get something, but that's not really going to help. Okay. It's a big number. It's going to be a really big number. So we're going to go ahead and subtract 6 from both sides. So we have negative 7w is equal to e to the 7th minus 6. Then I'm going to multiply both sides by negative 1 to clear that. Actually, how about we divide both sides by negative 7? No, let's keep going with this. So we're going to have 7w is equal to, and if I multiply by negative 1, we're going to have 6 minus e to the 7th. And I invite you, look at that in the calculator, right? It's 6 minus a really big number. This is going to be negative. Okay. Check that out. We could say 6 minus e to the 7th power. Okay, e to the 7th is huge. So negative, almost negative 1100 almost. Okay. And then we're going to divide both sides by 7. So we have w is equal to 6 minus e to the 7th over 7. And I'm claiming that's my answer, but I'm not claiming it just yet, because in order to make sure that's an answer, we have to check it in the original problem. Okay, so I'm going to go all the way back up at the top. Say, well, we've got 4 natural log 6 minus 7w is equal to, oh, plus 2, that's right. Plus 2 is equal to, I think, what was it, 30? 28, 30. Equals 30. Now, you say, well, wait a minute, this is negative. So can I take the natural log or not? Well, if we put it in, right, we have 6 minus a really big negative number. So it's going to be 6 plus a really big negative number, or really big number. So we're going to have a minus minus here. So 6 minus e to the 7th over 7. This is going to be 6 minus negative 10,090.63. That's from over here. Okay. So it's really going to be 6 plus this delightful looking number here. And that's going to be positive. That's something we take the natural log of. So now that I've looked at that number and I made sure that it works in the argument, then I'm okay with it. So we checked it. Okay. We checked it right here to make sure it worked. Okay, so it's an important last step that we're going to deal with is we're going to check our answer to make sure it works. Because you can get extraneous solutions here, and you want to make sure that you're not picking ones that don't work. Okay, so you have to check. Okay, with exponential functions, you don't. Okay, so if we have an equation that looks like a 5, and there's some kind of a function up here is equal to like a 7, and there's another function up here, we take logarithms and we work it out. Well, this started its life out as an exponential function. The domain for that is all real numbers. I'd be delighted if you checked, but you don't have to. Okay, it's not necessary to check it to make sure that there's not going to be any extraneous solutions here. Okay, whereas with logarithms, if you can end up with stuff that just doesn't work. Okay, so let's go ahead and move on here. And did I make sure that I got this? I did. Okay. Okay. Before we start this unit, there are 3 formulas you need to remember. Okay, so every one of my algebra classes, they all have these 3 formulas they have to remember, and they all deal with this. Now, this is not one of them. Okay, this was if you're going to go into banking, if you're going to go into accounting. Actually, accounting, this hurts my soul. They let you use tables for this. Okay, it does. I mean, you have to take college algebra as a prerequisite for accounting too. And then when you get to accounting too, I'm like, yay, we're going to use this. I'm like, no, here's a table. Like, why did you make me go through college algebra if you're just going to let me use a table? But this is for compound interest. Right? It's an important formula to be able to do and to know, because if you're ever going to go into loan sharking, right, you're going to have to be able to do this. Okay. It's also nice to know, like, well, this is how you're going to get screwed by the bank or by the credit card. But related to that formula, if we increase the compounding periods to all the time, so if we have continuously compounded, remember, that's not the thing that's really driving up the value. Your interest rate drives up the value, and the amount of time that you have it in there drives up the value. The fact that it's continuously compounded, that has some effect, but not as much as people might think. Okay. And that formula is A is equal to P. Now, this whole thing here turned into an E, right? That's how we came up with this number at the beginning, was we kept making N bigger and bigger and bigger to the RT. Okay, so this is the formula. We have the current amount, right? This is your principal. This is the initial amount, isn't it? Right? When you make a bank account, you put in your principal. That's the initial amount. E is our number. R. Be really careful, because they're going to tell you the APR as a percent, and your first job is to turn the R into decimal. Okay, the biggest thing, because this is people actually used to do compound continuous interest. They wouldn't do it if they were going to all of a sudden give their bank customers a ton of money. Okay, they're just doing it to compete against the bank across the street. And continuously compounded sounded strong. Sounded like a good advertising thing. So if you ever put in an R and it's like maybe you're saving for something for 5 years and you end up with like, I put $3,000 in and I got $5 million out in 5 years, like that is never going to happen. Okay, that does not happen. So don't look at that as a result and say, well, of course that was going to happen. Like, no, the only time that's going to happen, and I will do the word problem. It'll be like loan sharks are us is loaning money, and that's how it's going to work. Okay, but any like reasonable ABC bank, that's not happening. And then T in years. Okay, and I only try to draw that much attention to it because that really is the biggest mistake the students make with this one. Okay, but this is the formula for compound interest. This is one you have to remember. Okay, continuously compounded interest, you have to know this formula. Okay, the way I always remembered it was when I was in high school, when I was in my first year of community college, I lived at home, and all through high school, my mom would buy a shampoo called PERT, P-E-R-T, PERT. It's one of those 2-in-1 combination like shampoo / conditioner things. It's awful. I still remember the smell. It's terrible. It's not a bad smell. It just I don't like that smell. I still have it on good authority that this is sold like on the bottom shelf of Walgreens. So you can find PERT. It's a green bottle, and but that was the shampoo I had. So if you use it, God bless. But I did not like it. So that's continuously compounded interest. That's what you have to know. Here's the other formula. This is for biological growth. Okay, this isn't for people so much because there's a slightly different formula we use for people. I think we get to it in the next section, but this is like for bacteria or for rats, mosquitoes, vermin, that kind of stuff. Okay, small things. Okay, if we have biological growth. Oops, sorry, shouldn't be a 0 there. Put the 0 in the wrong spot. Okay, so we have the population at a time, right? So the current amount. We have an initial amount, E, of course, because that's our favorite number. Okay, R is your growth rate, and then time is or T is time. Okay, now if you're talking about like rabbits and you have a growth rate over years, time is going to be in years. If you're studying bacteria multiplying in a petri dish and you're studying your growth rate in hours, then time is going to be in hours. So time is consistent with whatever units the growth rate is. Okay, so growth rate for units. Okay. All right, and then the last one we have is radioactive decay. Your book uses Q, so Q of T is equal to Q sub 0 E to the KT. Your book does this, and I don't agree because it messes up with my pattern. Okay, the book explicitly puts a negative sign there. I know my K is going to be less than 0 when I work this. So I know that that's going to happen because it's a decay rate rather than a growth rate. But your book puts in a negative sign on the outside there. I don't recommend it. I just recommend you like allow for K to be negative, and then the negative sign sorts itself out, and you don't have to track it. So I would suggest that you do it that way. But there's not just one great way to do it. Okay, if you want to keep the negative sign there, you be my guest and do that. But this is the quantity at current time, or at some time. This is your initial amount. E is again our favorite number. K is our decay rate. Okay, and then time, or t is time. Again, see the decay rate. Okay, so t is time. See decay rate for units. Okay, so if you're talking about something that's made in the lab and decays like in a second, then your decay rate's going to be in seconds. Maybe in hours for other radioactive material, but a lot of times it's going to be in years. Okay, so if its decay rate is in years, then we're going to be talking about years. But there's some elements that they decay in very quickly. Okay, so your time is going to be in seconds, right? Maybe milliseconds, but that's how they measure that. So to summarize, right, we have three formulas. We have A equals PERT. We have P equals P sub 0 e to the RT. And we have Q equals Q sub 0 e to the RT, or KT. Okay. Now, if we were together, I would ask you, expect an answer, how many formulas do you see? And I really hope you look at that and you're saying, I see one formula, because that's the point. Okay. All of these categories, all of these different scenarios that we're going to be working on pretty much use the same formula. They just spell it different. Okay, they use different letters, but these are all the current, or these are all the amounts at a certain time. These are all the initial amounts. The rates, right? Decay rate because it's negative, growth rate because it's positive, interest rate because it's positive, and then time. And for interest rate is annual percentage rate, time is in years, right? Growth rate, if it's within, days, then time is going to be in days. Decay rates, right, usually in years, t is in years. So it just depends on whatever your decay or growth rate is as to do your times. But I don't care how you spell these things, okay? If you just want to remember this formula because it's the shampoo and it's easy to remember, and you use that for everything, I have no complaints. You go right ahead and use that, okay? Your chemistry teacher might be a little bit upset, but you're still going to get the right answer. So don't worry about how you're spelling it. At least with me, don't worry about how you spelled it. Okay, so I say it's three formulas, but honestly, it's one formula. Okay, so that's our exponential. This is our exponential model. There are other exponential models that we use for different things. You are not required to memorize them. If I'm going to pull out something like how does something cool, right? Because cooling is exponential decay, right? I'm going to hand you that formula. So don't worry about trying to memorize all of them. You have to memorize these three, which really you have to memorize one. Okay, I remember I took electronics so many years ago, and we had Ohm's law. So we did not necessarily have algebra as a prerequisite for this class. And the guy who's teaching it, to his credit, he kind of knew the population he was dealing with. So we were told we had three formulas to memorize. And I looked at that. I was like, really? Three formulas? He's like, yep, three formulas. You got to know them all. Actually, I think he had other permutations to work with other things. Like there was like ratios in here as well. I was like, why can't you just use algebra? He's like, because people don't know it. Like, okay, I'm going to use algebra. I'm not memorizing your formulas. I'm memorizing this one because there's no fraction in it. Voltage equals current times resistance. That's what this is. Okay. I'm not going to ask you to recreate that or anything like that. But the same thing kind of goes. Like generalize this to one thing, and then realize they're really all the same formula. Okay. We have to talk about one more thing before we actually do this problem. Well, two more things. One's easy, one's a little bit, I don't know why it's harder, but it is. Okay. So as we're going through this problem, okay, physicians often treat thyroid cancer with a radioactive form of iodine called iodine-131. Okay, so I-131. This 131 has nothing to do with the problem. It might as well be blue iodine. Okay, it's the type of isotope because different atoms can have different numbers of neutrons in them. It's just the kind of iodine that it is. It's a radioactive form. That's all it's talking about. So this 131 has nothing to do with the problem. We don't care about the fact that it's 131. Don't write that number down. Okay. Well, don't write it down and expect it to have any meaning because it's not. Then we have the half-life of this thing is approximately 8 days. Okay, so this was the first one because a lot of people get this number mixed up. Okay, I remember I would teach statistics and I would say, the Nimbus 2000 broom would do something, and people would put that 2000 in there like it's going to mean something later on. Like, no, it's just like a neat number that they used on the broom. It's not. It doesn't mean anything. Oh, okay. Half-life. This is the amount of time it takes for half of this to be left. Okay, so a half-life is the time it takes for half to remain. Okay, I don't know if the story I'm going to tell you is true, so take this with a lot of salt. But this is one of the ways I remember it. But when I say half of it left, I mean it doesn't evaporate into nothingness, right? It's not doing like E equals MC squared. I mean, it is a little bit. But what's going on here is there's a whole part of chemistry, radioactive chemistry. This will spit out, this will kick out some kind of a particle. Like if it kicks out an alpha particle, it'll lose a couple of protons and neutrons. And this turns into what they call daughter isotopes. Okay, so we're not going to study that. We're not going to worry about it. But this molecule would be gone, or this not molecule, this atom would be gone. It would turn into two other atoms, okay, and release some energy. So when I say it's half of it's gone, I mean not that we have half of the mass left. It's just half of the mass of this stuff. Okay. So when I was in my, I don't know, 18, 19, 20, right, and you discovered drinking. Okay, not so much anymore, I guess, but back when I was 18, 19, and 20, that was like a really important thing. And, well, you drink too much and then you would throw up. And sometimes you drank way too much and you'd throw up a lot, like several times. Some of you I know have had this experience, but you may throw up and you eventually get down to dry heaves. But the process that the throwing up, and I don't know if this is true. I've not been able to look it up or verify this, but I was told that your stomach empties half of its contents every time you throw up. So it's a half-life problem because, if you have a liter of alcohol, vodka, in your stomach, and then you throw up, then you'll have half a liter. And then you throw up again, and now you'll have a quarter of a liter. You'll throw up again and you'll have an eighth of a liter, and then so on until there's not enough matter in there for your stomach to do anything about it, and then it hurts. So half-life, right, is when half of the stuff is left. So that's an important thing to remember because a lot of the problems are going to have half-lives in them. Okay, so let's see here. Radiological half-life is approximately 8 days. But the biological half-life is 4.2 days. Oh, that's interesting. That's usually for the metabolism. Okay, so half-life, that's 8 days. Your biological half-life is 4.2 days. I don't know what we're going to do with those numbers yet. Yeah. So for a patient treated with 100 millicuries, okay, it's actually not a standard measurement anymore. It's still used a little bit, but not as much. T days, see, they give us a formula. Okay, so this is T days is given by 100 times 2 to the negative 4.2. Okay. State law mandates that a patient stay in an isolated hospital room for at least 3 days after ingesting this stuff. Determine the radioactivity, that's the millicuries. Okay, at the end of 3 days, round to the nearest whole unit. See, I went through all that with all the formulas, and they just give us one. So since they gave us one, we're going to take it. Okay, and we have negative t to 4.2. Okay, so notice the half-life was given to us in days. T is going to be in days. Okay, so state law mandates that the patient stay in an isolated hospital room for 3 days after ingesting it. Determine the radioactivity level in 3 days. The 100 is the radioactivity. This is the millicuries, right? So we're going to say, oh, that's 100. And we're going to say 2 to the negative 3 over 4.2. And we're just going to calculate that. That's all they want us to do with this one. How boring. For all of that. Okay, 100 times 2 caret. Now, since we have some arithmetic up here, we have to use parentheses. Okay, if you don't use the parentheses, it will do 2 to the negative 3 and then divide the whole thing by 4.2. It's not going to be the same number. Okay, divided by 4.2. So our radioactivity level is going to be 60. How many decimal places did they want? Round to the nearest tenth of a day. Okay. Wait, that's not right. Round to the nearest whole unit. Okay. So in this case, 60.95, we're going to call that 61. Okay, so we have 61 millicuries here. All right. Let's see what we have here. Let me show you. If you don't do that, you won't know. Okay, you won't know. Because these numbers don't have a lot of reference for me either. Okay, so if you forget the parentheses, you get a very different number. Okay, so be careful about that. Be careful with those parentheses because they very much change your answers. Okay, so let's see here. The nearest whole unit. Part 1. Radioactivity at the end of 3 days is 61 millicuries. Okay. I usually just use like grams. Okay, so I don't worry about how much radioactivity. It's like there's a microgram of it. Okay, or there's a 2 kilograms of it. Okay, what are we talking about next? Okay, after the patient is released from the hospital, the patient is directed to avoid direct human contact. It sounds like how do they manage? Until the radioactivity drops below 24 millicuries. For how many days will we have to be, after leaving the hospital, will the patient have to stay in isolation? Around to the nearest tenth of a day. Okay, so here we have it, right? We have R is equal to 100 times 2 to the negative t over 4.2. What did they want? They want the radioactivity to be 24 millicuries. So we're going to put in 24 here is equal to 100 to the negative t over 4.2. So let's go through and deal with our logarithms, okay? So the first thing I'm going to do is try to clean this up a bit. Okay, so instead of that, we're going to have 0.24 is equal to 2 to the negative t over 4.2. Okay, so we don't have anything in front of it. There's no pluses. We've got a clean exponential function here. So I've got a variable in the exponent position. How on earth should we get it down? Take a logarithm. Does it matter which one? No. If we could take log base 2, we probably would, but since that's not on my calculator, I'm not going to worry about it. So let's go ahead and take a log. So log of 0.24 is equal to the log of 2 to the t over 4.2. The whole point of doing that is that this can now come down on the baseline because of our rules of logarithms. So we have log of 0.24 is equal to negative t over 4.2 times log 2. Okay, this is 0.24. And we're just going to solve for t. So divide both sides by log 2. Divide both sides by log 2. We have negative t over 4.2 is equal to log of 0.24 over log 2. Let's multiply by 4.2. Let's multiply by negative 4.2. All right, so that negative will go away. That 4.2 will be on the other side, so we have negative 4.2. See, I can hear you now. You're like, wait a minute, shouldn't this be negative? This is under 1, right? Anytime you take a logarithm of something that's smaller than 1, you're going to get a negative number. So that's going to work out okay. Right? So let's go ahead and see what that turns into. And I'll do it carefully so that we can see. Negative 4.2 times log of 0.24 and the parentheses divided by log of 2. This one you don't have to end the parentheses on, but since we already did it, I'll do it again. Okay, and we got t is equal to 8.647 and some change. They said round to the nearest tenth of a day, 8.6 days. Actually, I have a feeling that if you tell that to somebody, they're not going to know what 8.6 days is, so 8.5 is the answer I'd probably give the patient. I don't know, remaining in social isolation for 8.5 days, it seems unfathomable. Wait a minute, what do you mean try again? 8.6, 8.6. Oh, after leaving the hospital. So how long were you in the hospital for? We were in the hospital for 3 days. 5.6. Sneaky. Okay, there we go. Okay. This is also why when I ask these questions on an exam, like if you said 8.6, I'm just gonna I'll say, hey, you forgot, and I'm just gonna mark it right. I'm not gonna pounce on you for that. That's too small. Okay. Let's see. Can we get to a bigger one? 15. Do we have my favorite problem here? Sorry, I'm looking for one specific problem. I think it's probably in the next section now, so. Oh, that's a good one. No, they don't have my favorite problem in this one. All right, well, let's work on the problems we do have. Okay, they don't make you memorize formulas at all for this one. I don't know. Maybe I'll have to reconsider. Okay, caffeine occurs naturally in a variety of food products, such as coffee, tea, and chocolate. Caffeine. The kidneys will filter out the blood and remove caffeine and other drugs to the urine. Biological half-life is approximately 6 hours. If 1 cup of coffee has 120 milligrams of caffeine, then the caffeine in milligrams remaining after T hours will be this thing. Again, they give us the formula. So if they give you the formula, see, I always think about this as, and people are like, oh, it's a word problem. I'm like, no, this is a problem with words in it. It's not really a word problem. They give you the formula. Right? Word problems are when they're like, figure out the best area for this. Like, wait, I have to come up with a perimeter and an area? Yeah, that's a word problem. Okay, so there's our formula. Okay, and again, be real careful. Don't put this with this. Okay. How long will it take the caffeine to drop below 60 milligrams? Round to 1 decimal place. This is in hours, right? T is in hours. Because the half-life was in hours. Okay. So what did they want to know? They wanted to know below 60? Really? So we'll do this one dutifully, as they said. But I just, so we can get practice with the process, but I just want to point one thing out. Oh, okay. But I want to point one thing out before they do this. They said the half-life is 6 hours and 60 is so conveniently half of 120. Like, really? Come on. This is going to be t is equal to 6. We don't have to do this. I do that too every once in a while. It's not my intent to give you guys a problem that is obvious. I try to come up with problems that are you actually have to do the work on. But every once in a while, I look at it, I'm like, oh, I can't believe I did that. Okay, but let's solve for t. Just to get practice with the algorithm, just to get practice with how to do this. Okay, so if we get something other than t is 6, then, we'll know something's up. Okay, so the first thing I'm going to do, I'm going to take this coefficient, I'm going to move it out in front. Okay, so at this point, right, we've got 1/2 is equal to 2 negative t over 6. Okay, just by moving this thing out, moving this coefficient away. So now we have a variable that's in the exponent position. How do we deal with that? Now we're going to take a logarithm. So I'll use this log of 1/2 is equal to log 2 to the negative 6t over 6. Okay. So what we're going to do now is we're going to pull this down in front because that's one of our rules, right? We're going to pull this in front. So we're going to say this is the log of 1/2 is equal to negative t over 6 times the log of 2. Now, I'm going to show you something neat, and this is like what makes logs so magical. 1/2 is really a fancy way to write 2 to the negative 1, right? That's reciprocal. And then we're going to do the same thing with this one. We're going to pull that down in front because it's an exponent, so we're allowed to do it. So it's negative 1 times log 2 is equal to negative t over 6 times log 2. So now we're going to divide. Right? We're going to divide everybody by log 2 because that's what we have here. Okay, so we have negative 1 is equal to negative t over 6. We're going to multiply by negative 6, and we get t is equal to negative 6 times negative 1. T is 6, which is great because we knew that already. Okay. So that's, by the way, this trick right here, I shouldn't call it a trick, but this little operation, you will see that in so many science books, it's going to drive you nuts. So realize, right, we have half-life, where we usually have a natural log of 1/2, and immediately, all of my books always did this, was that, which was negative ln 2. So much so that they just wrote this down instead. Okay, it occurs very often. You're going to see it a lot. Just realize when you see this negative natural log 2 or negative log 2, this is the process they went through. Okay, but I'll remind us of that when we find another one. Okay, so 6 hours, decimal place. So Laura has trouble sleeping if she has more than 30 milligrams of caffeine in her bloodstream. Seems oddly specific. How many hours before going to bed should she stop drinking coffee? Round to 1 decimal place. Okay. This is two half-life, isn't it? Right? We went from 120 to 60. Half of 60 is 30. So we have 2 half-lives. The answer is going to be 12. Okay, we have 2. Again, I wish they picked a slightly harder problem. So for 2 half-lives, right, we have 6. We have another half-life. We have 12 hours. Okay. So the time I go to bed, about 11 o'clock, 12 o'clock. God, if I had to stop drinking coffee at noon, I wouldn't know what to do. All right, let's see what we have here. It'd probably be healthier. Get better sleep. Okay, so here we go. We have 30 is equal to 120 times 2 to the negative t over 6. Okay, we're going to make this clean exponent. So 2 negative t over 6 is equal to 30 over 120. Okay, dividing both sides by 120. So that's 30 over 120, like that's a quarter. We could test that out. 30 over 120. 25, good. Is equal to 2 to the negative t over 6. So this is, we have a variable in the exponent now. So what we're going to do is we're going to take logarithms to get it down. So we have ln of 1 over 4 is equal to ln of 2 to the negative t over 6. This bit comes down because it's an exponent. So we have negative t over 6 natural log 2 is equal to natural log of 1 over 4. And you know, I am going to do this. I'm going to say, you know, natural log of 1/4 is really, right, is really that. I'm going to go one further. I'm going to say that 4 is 2 squared. Okay, so this is negative 2 natural log 2. Okay, so we're going to have negative 2 ln 2 is equal to negative t over 6 times ln 2. Let's divide both sides by ln 2. That's the reason I went that far with it, because I wanted that to cancel. Okay, is equal to negative t over 6. We're going to times both sides by negative 6. 6 times 2, that's 12, is equal to t. All right, so you don't quite, I try to make pains to not make them that easy, because I really don't want you to just write down by inspection t equals 12. Technically, that's what we did at the beginning. Okay, so I try to make you work for it at least a little bit. If I was going to ask you like a bunch of multiple choice, that would be 12 hours, not 4 hours. All right, there we go. Okay. Okay, let's work on this one. All right. So this is Newton's, this technique, this process, this formula is going to be called Newton's law of cooling. Okay. So this is what we're talking about. I have to go back on my, you have to memorize these formulas idea, because you didn't have to memorize one yet. Okay. The pie comes out of the oven at 330 degrees. It's placed in a cool, this is the temperature of the environment. Okay. The temperature of the pie in Fahrenheit after t minutes, so this is going to be in minutes here, is given by right there. Okay. So our current temperature, right, this is current temperature, temperature time t. You think the capital T's and the little t's are going to be bad? Just wait. Here's a spot in differential equations. We use t, and tau because we can't get enough t's. Okay. So capital T, little t, and the Greek T, because we don't have enough. And that's still the worst notation that we have. Okay, so we have t is equal to 75. That's kind of nice that they give us that. Okay, this is the, if you see this in another book, they'll call that T sub E. That's the temperature of the environment. I don't think your book is going to make you go through this, though, which is fine. 255. Where did 255 come from? Well, that's 330 minus 75. Okay, that's where that came from. E to the negative 0.015. That's a constant related to the things. Okay, so some kitchen somewhere was very careful in their temperatures and trying to figure that out. Okay, come back. Where'd you go? Okay. The pie is cool enough to cut when the temperature reaches 110 degrees. Determine how much time this will take. Okay. So when T equal 110. Okay. It's really kind of cool. The FBI has like an entire lab of doing bizarre things to bodies because they use temperature for like time of death. But this only works if you have a constant environmental temperature. So they do all sorts of research, like what happens if you put a body in the trunk of a car. It's kind of going up and down depending on the time of day, all of that fun stuff. But if you're doing like SCI stuff and you're lucky enough to like get somebody very quickly, like overnight, and then you have a constant environmental temperature, then here you go. This is what you do. And this is true. They have tables for them. Okay, clear. 110 minus 75. So you can impress all your friends watching CSI. You can say, they use Newton's law of cooling to figure that out. I'm sure they'll be very impressed. 0.015T. There we go. And we're just going to solve this like normally. We're going to clean this thing off, right? So T55. Okay, so I'm going to have 35 divided by 255. And I'm going to go ahead and make it neater than that. 751s. Okay. Hey, we've got a variable in the exponent position. What do we do about that? And we have an e. That means we're going to use natural log. So we have natural log of 751st is equal to the natural log of e negative 0.015t. We're going to pull this down in front. We have negative 0.015t times the natural log of e is equal to the natural log of 751st. Now the natural log of e, right? That's log base e of e equals what? Well, e raised to something is going to give us back e. So that's kind of a silly way to say 1. Like, yes, it is. So e to the 1 is e. Negative. All right. And then we're just going to divide by this number here. Divide by negative 0.015 divided by negative 0.015. So t is equal to, we're just going to type it in. So natural log 751st. That's 751st. Okay, divided by 0.015. Oh, okay, that makes sense. Okay, so it's not negative because this one's negative and this one's negative, so it's going to be positive. We have 132.394 and some change. So remember, t was in minutes. Okay, so after about what, 2 hours for the pie to cool is about the time it's good enough to cut. Should make reasonable sense. I don't know. I don't keep my kitchen at 75 degrees. So. Well, I will in August. I'm not going to be making any pies. Okay, so what do they have us do this? What do they have us time us with? after minutes. Sits there with a stopwatch in minutes for the pi to cool. So that's a Newton's law. I generally don't ask this kind of a question because it's a little bit more involved than students are really comfortable with. I mean, I could ask it as one of them, but if I'm going to ask, if I ask two these types of questions, one of them is almost always going to be like the radioactivity one, and then I might ask one that's a little bit harder. And I'm going to rest that. Let's do a couple more problems and see if we can't. Actually, let's not. Let's call it a day. All right. Let me stop recording and then I'll go with